Welcome back to Quick Soil Mechanics Lessons with Brian. Continuing with lessons in pore pressure. Lesson 3, the myth of hydrostatic pore pressures, part 3. So effective stress, it's all about the pore pressure. So for effective stress, you subtract the pore pressure from the total stress. So knowing and understanding the pore pressure is very important. So just to review hydrostatic pore pressure, there's no drainage. We have our tank of water, the water surface. We put an isolated tip piezometer into there, and that isolated tip piezometer is going to tell us where the water surface is. It's got a 1-to-1 pore pressure distribution. So if you go down 1 meter, you have 1 meter of head, 2 meters, 2 meters of head, and so on. Now, if we have tailings and they are drained, we have a different thing going on. So we may have a pore pressure distribution that's like this. We have double drainage, right? The top and the bottom. And we may have pore pressures in the middle. And if we have an isolated tip piezometer, it is going to have that kind of pore pressure at that depth. And so it's going to tell you that this is what the pore pressure is at that point. So that isolated tip piezometer does not tell you the location of the phreatic surface. It tells you the pore pressure at that point. And that's what most good isolated tip piezometers do, like a vibrating wire piezometer. It tells you the pore pressure at a point and not the level of the water table or water surface. So that's a very important thing to remember. So in our last video, we talked about Gibson's theory of the progress of consolidation and a clay layer increasing in thickness with time. And the paper describes the one-dimensional consolidation of the clay layer, which increases in thickness with time. And the pore water pressure is generated by increasing the weight of the material and the length of the drainage paths, which change with time. Okay, and that is a lot like what tailings do. Tailings accumulate and increase in thickness with time. The drainage path is changing all the time, probably increasing. The properties can change with depth. If something's going on in the mill or the ore body, there can be changes, and also spatially. So let's get back to our little spring and dashpot analogy of an odometer. And remember, at time t equals 0, the excess pore pressure is uniform and equivalent to that load that's being applied to the top. But if we have drainage ports and we let some pore pressure dissipate, then we've got this dissipation of the top and the bottom. We've got this parabolic shaped dissipation that goes on and continues to dissipate over time unless something else changes. Well, in tailings, it doesn't work that way. We have accumulating layers. So we've got a layer that's deposited. We put more tailings down. So the tailings increase with thickness with time, and the drainage paths are changing. And so if the rate of accumulation of the tailings exceeds the ability of the tailings to dissipate the pore pressure, excess pore pressures can result. Those are pore pressures that are in excess of hydrostatic. There's a really good paper by Charles Ladd that came out several years ago called Stability Evaluation During Staged Construction. And everybody should read that paper. That's filled with some really amazing work. One of the things that's in that paper is this illustration of a tailings facility. It's an upstream constructed tailings facility. And there's a lot of stuff going on in here. But there's sand and gravel at the base of the facility. And you can see toward the left-hand side where it says slimes, there's almost kind of like an elongated bullseye going on there. So the water surfaces at the top there, and then the pore pressure increases, it's pressure head in feet. So you can see 20 and 40, and then it says slimes, and then it goes 40, and then it goes 30. So it's decreasing toward the bottom. And we've seen that before. Remember with our odometer test. So we've got high pore pressure in the middle, or higher pore pressure in the middle, and lower at the top and the bottom. And I've seen this in real life, and this is a real life example that's given by lab. But I had a project that had pore pressures that were very much like this bullseye. And in the middle of the bullseye, they were actually in excess of hydrostatic pressure. And that meant like artesian pressures. And so we decided to put some wick drains into the facility, and water came up to the top of the surface there through the wick drains, so that excess pore pressures were being dissipated. We put the wick drains all the way to the bottom so that they could dissipate at the bottom as well. And I'm familiar with a couple of other tailings facilities where they've used wick drains to expedite consolidation. And in those cases, those wick drains wouldn't have worked unless they had excess pore pressure, because the water was coming out of the top of the wick drains. So in all of these cases, there is no such thing as hydrostatic pore pressure, and you should always assume that hydrostatic conditions don't exist in a tailings facility unless you know otherwise. But getting back to this diagram here, you can tell that there's not just one or two piezometers that are giving this information. There's an array of piezometers, and that's what we had also on the facility I was talking about. We had an array of piezometers, both with depth and with on the x-axis in this diagram. And so we had them in a grid type pattern so that we could see what was going on and how the pore pressures were dissipating from the wick drains, but also the pore pressures would rise as they built on top of the tailings. So again, don't assume that there's hydrostatic conditions, and don't assume that any single piezometers is telling you the level of the phreatic surface. It could if you have hydrostatic conditions, but most often you should assume that there's not hydrostatic conditions. Well, that's been a lot for today. I think we will call that quits there. Thanks for hanging in there with me, and we will look forward to the next video. Thanks again.